All right, and welcome back to our video lesson series from Unit 8.5, which is about stoichiometry. This is our fourth lesson. And in our previous lesson, you learned that percent yield was equal to the actual yield divided by the theoretical yield, and then multiplied by 100. So what does this mean? This means you go to a lab bench, you do the chemical experiment, the chemical reaction, and you produce an actual amount of product. And you weigh it, and that is the actual yield. The theoretical yield, in the previous lesson, we were giving you the theoretical yield. But in this lesson, we're going to figure out, well, where does this theoretical yield number come from? And the answer, my friends, is that it comes from the stoichiometric calculation. Okay, so that's why this is considered advanced, because you have to do the calculation, the stoichiometric calculation to determine theoretical yield in order to find percent yield. Okay, so let's take a look at an example of how to do this. If this reaction below uses 20.0 grams of lithium hydroxide is LiOH. Right, so we're saying that this reaction here uses 20.0 grams of lithium hydroxide. And then it says there's an excess of potassium chloride. That's KCl. So we have lots of this. And all that means is you can ignore this substance. Okay, so when you have the excess reactant, you're just ignoring it, and you're going to be focusing on the other reactant. Okay, so that information we're ignoring. The question is asking how much lithium chloride could theoretically be made. So lithium chloride is, of course, LiCl, and we are wondering how much of this lithium chloride could be made. All right, so when we find the answer to that, that is our theoretical yield. All right, so to answer this, this is a gram to gram stoichiometry problem. So to do gram to gram, as you recall, you start with the given quantity. Our given quantity was 20.0 grams of LiOH. It's important to note that you want to have the quantity, the unit, and the identity to start. Set up your brackets. To do gram to gram stoichiometry, we are going to put grams of LiOH in the denominator and moles of LiOH in the numerator. 1 mole of lithium hydroxide, if we add up the mass of a lithium at 6.9 to the nearest tenth, oxygen is 16.0, and hydrogen, of course, is about 1.0. So I'm just going to jot this down here on the side. Lithium is actually 6.94, oxygen is 16.0, and hydrogen is 1.01. So that's the molar mass. So just a quick side calculation, 6.94 plus 16 plus 1.01. So we get a molar mass of lithium hydroxide to the nearest tenth to be 24.0. Okay, going to the nearest tenth, rounding up. All right, so if we stop the problem there, grams of lithium hydroxide cancel, leaving us with moles of lithium hydroxide. But we're not done, because we're trying to find grams of lithium chloride. So our next fraction is going to have moles of lithium hydroxide, and it's going to have moles of lithium chloride up in the numerator. And so the numbers that go here are the coefficients from the balanced equation. So we do see that this is a balanced equation. It's 1 to 1 to 1 to 1. So mathematically, there's no effect here, but this allows us to validate that we are canceling out the appropriate units. So lastly, we're going to convert moles of lithium chloride into grams of lithium chloride. And if we do the molar mass there, lithium is 6.94, chlorine is 35.5. If I add that up, right, 6.94 plus 35.5, I get 42.44. Rounded to the nearest tenth, 42.4 grams. All right, so all the units cancel with the exception of grams of lithium chloride, and now it's just time for my calculator work. So starting with the 20, I'm going to divide by 24, multiply by 1, divide by 1, so I'm not going to do anything in my calculator, and I'm going to multiply by 42.4. All right, so 3 sig figs in my original measurement, so I'm going to honor the 3 sig figs here, so I've got 35.3 grams of lithium chloride. That's my theoretical yield. Once I know theoretical yield, I can address the next question. After doing the above experiment, the reaction produced only 6 grams of lithium chloride. So they're telling us that the actual yield was 6 grams. And you're meant to calculate the percent yield of the experiment. So the percent yield is equal to the actual, which we've defined as 6.0, divided by the theoretical, which was the answer to our stoichiometry problem, so 35.3 grams, times 100. In our calculator, it's 6 divided by 35.3, multiplied by 100, and we get 16.99. Let's round that to 17.0% yield. Okay, not a very good percent yield. It's like getting a 17% on a test. But there it is. That's the numbers that make sense for that problem. All right, let's try one more problem together, and then you can try a problem set. In this problem, they are asking what is the theoretical yield of iron 3 chloride. Right, so iron 3 chloride is FeCl2. That's this stuff. We're trying to find the theoretical yield of this. If the reaction below uses 34 grams of iron 2 bromide, okay, so that's this stuff, and they're telling us it's going to use 34.0 grams of that, and an excess of potassium chloride, so we have lots of this, and remember, when we have lots of it, we are going to ignore it. So our job is to do a gram-to-gram stoichiometry problem to figure out the theoretical yield of iron 2 chloride. So setting up this problem, we start with the quantity, the unit, and the identity of the substance we're starting from. And setting up our gram-to-gram problem, we've got grams of FeBr2, moles of FeBr2. 1 mole of this substance, if we take a look, iron 58 or 55.8, bromine 79.9, but 2 of those. Okay, and so when we add that up, 79.9 times 2 plus the 55.8, we see the molar mass of this substance is 215.6. So that's the molar mass of iron 2 bromide, 215.6. My next step is to cancel out the moles of FeBr2, and I'm going to use the mole ratio from the balanced equation of FeCl2. And if we take a look, this is a ratio of 1 to 2 to 1 to 2. So the coefficient in front of the FeBr2 is 1, and the coefficient in front of the FeCl2 is also 1. Okay, so mathematically, no effect, but that's going to allow our moles of FeBr2 to cancel. Lastly, in our gram-to-gram stoichiometry problem here, I'm going to cancel out moles of FeCl2, and I'm going to convert that to grams of FeCl2. If I do a side calculation for the molar mass of FeCl2, we know iron is 55.8, chlorine is 35.5, but there's 2 of them. So let's see, 35.5 times 2, of course, is 71, plus 55.8. So our molar mass for iron chloride is 126.8. And of course, that's it, the mass in 1 mole. I'm going to take a look at my units canceling out. Grams of FeBr2, cancel. Moles of FeBr2, cancel. Moles of FeCl2, cancel. leaving us with grams of FeCl2. All right, now for the calculator work, I'm going to start with 34. I'm going to divide by 215.6, multiply by 1, divide by 1, so nothing to do in our calculator, and then multiply by 126.8. To 3 sig figs, our original measurement 3 sig figs, so this looks like it's going to be 20.0. 20.0 grams of FeCl2. So that's our theoretical yield. The question is now asking what is the percent yield of iron 2 chloride if the actual yield is 4 grams. So percent yield is equal to the actual yield of 4.0 grams divided by the theoretical yield of 20.0 grams multiplied by 100. The math in your calculator becomes 4 divided by 20 multiplied by 100 to put it into percent form, and we're going to go with 20%. I'm going to put a decimal point visible there to reflect that this should have 2 significant figures. So the percent yield is 20%. A little bit better than the previous problem, but still not a very good percent yield. But that's what supports the numbers. All right, the back side of this is a problem set. There's a couple problems for you to try right there. And give those a shot. Check your work. See me with questions, and I'll see you back in the classroom.